Hey guys, today we'll be talking about trees, and it's the most asked topic in the interviews. So we'll be covering it within a short period of time. At least we'll try. So let's get started. Uh, so we'll talk about trees in DSL, and there's something called as binary tree. The word itself says the meaning. Binary means either this is a node, this node either can divide into two parts or one part or zero parts. That means it can maximum divide it into two more nodes. So that is called binary tree. So now let's come into terminologies. So this is called root node, where all the division starts from. And if you take this root node, then these are called children nodes. These are called children because this root node divides it into two more nodes, and if it divides it into two more nodes, those nodes are called as children. So if you take here more nodes like this, these are also children nodes with respect to this node, right? uh, what else is there? This is called as leaf node. Why leaf node? Because it's at the end and it doesn't divide it into further nodes. And this you can say is null. This is null if you code it in C++ or Java, right? And two more important terminologies where if you take this particular node, let's say this is messed up, let's take this node. If you take this node, then this is called as an ancestor node. This is called an ancestor node. And let's take where's my duster? Over there. Okay, so I'll take another tree. It was pretty messed up here. So yeah, if we the last terminology is remaining where if this is a tree, then uh, if you, let's divide it into more parts. So if you are in this node, if you are at this node, then uh, this is called a subtree, where the this whole tree is called a subtree. If you uh, let's say if you are here, this whole node will be a subtree, right? So that's it. And let's move into traversal part, like I mean depth first search, breadth first search, all those things, right? So yeah, there I have my duster. Okay, so depth first search, which is DFS, right? What happened to a marker? Okay, fine. This first one is called in order. Um, in order search, where if you have say this tree 1 2 3, then this left node will come first, then the root node will come, then the right node will come. It searches in this according order. So this will be 2 1 3. Now this was pretty simple. It's just left, root, and right. What if we have another subtree here? Then it will get complicated. Let's see now. Okay, so if you have a tree 1 2 3 4 and 5, so First will be left, which will be 2. Then you will go to the root node, which is 1. And here we have the right node. Now in this right node, you have to again go to the left, which means the left part of the right node, which is 4. 4 will be printed. Then you'll go to the root node of the right part of the node, which is 3. Then you'll go to the right part of the right part of the node, which is 5. And this was the same for 2 if it was on the left. And that's it about in order search. So let's move to the next thing, which is pre-order search. Let me rub this again. Okay. So in pre-order search, uh, we take the root node first. Take the root node, then left node, then right node. At last, I will tell you a trick to how to remember all this. I mean, root, left, right, what comes first, and yeah. So let's get into this. First, let's continue. This is 1, this is 2, 3, 4, 5. So first will be root. First will be root. So root will come first, which is 1. Then the left part will come, which is 2. Then the right part will come. Now in the right part, again the same thing. Now in the right part, we have uh, the root node first. So it is gonna be 3, and then it will be left, which is 4, then 5. Uh, right part of the root, then left part of the root, right root, and finally the right part of the right root. We follow like that. Uh, let's move on to the next, which is the final one, which is nothing but uh, post order search. Post order search, where uh, sorry, where you have the left one first, then the right one, then finally the root one, obviously. Okay, so the left one will come first, which means 2 will come first, then the right one. Now in the right one, again the same thing, the left part of the node, which is 4, then the right part, which is 5, and then the root node, which is 3. And now all together, the whole node, we have to see with this point of view, the whole node, which is uh, the root node of the whole node, which is 1. This is the final one, 1. That's it. That's it about depth first search. Now let's move on to the breadth first search. Okay. Okay, so we have the BFS, which is breadth first search. This is very simple, guys. Let me tell you. This is a node. This is a node. This is another node. This is another node. Another node. Another node. 1, 2, 3, 4, 5, 6, 7. Okay. So let me tell you one terminology. We call this a level. This whole thing is called a level. This whole thing is called a level. This whole thing is called a level. Now in breadth first search, we just go through levels. Like this first level, one will be printed. Then this will go to this level when 2, 3 will be printed. 2, 3. Then it will go to the third level, which is 4, 5, 6, 7. As simple as that. This is very similar to level order traversal. Yeah, level order traversal. Okay, that's it about traversal. And there are more types of binary series. So let me see the types. We'll go through the types first. So first one is full binary tree. Full binary tree, where in full binary tree we have a tree. We have a tree. Now in this full binary tree, uh, all the what do we say? Okay. It has two or zero or two children. That means this particular node at least has two children. Not at least, has two children. Has two children. Has two children. Now it could have been something like this. This is also a full binary tree. But it can't be like this because this node divides in. This node has only one children node. It should have at least. It should have zero or two children nodes. So yeah, this is full binary tree. And next up we have complete binary tree. Complete binary tree where let me take a binary tree first. Okay, so this is a binary tree, and all the levels are complete here, which means it's maximum. Yeah, it can divide into two children, right? At max. So it's maximum, and the levels should be complete except the last level, where in this case it's complete, but it could have been something like this. The last level could be incomplete, but you have to keep one thing in mind, which is it should be as left as possible. Now what do you mean as left as possible? Like, see, this is a node. It could have been divided like this. Let me take. Okay, so this is a node. It could have been divided like this. So this is the right part of the node. It's divided into in the right side. But what does it say? It should be as left as possible, right? So it should be like this. And it can't be like this. Can't be like this. It's wrong. It's wrong. Now uh, I want you guys to comment me down then whether this particular node, sorry, what did I tell? This tree, whether this tree is a complete binary tree or not. This is the problem for today. And moving on to the next one, which is perfect binary tree. Perfect binary tree, which is perfect. Literally says the word perfect, which means everything should be complete. Every level should be there. This is a perfect binary tree. It could be like this. It could be also like this, right? This is perfect binary tree. It can't be incomplete like this. It's pretty simple. And the next one, last two are remaining, which is degenerate binary tree. Degenerate binary tree. What do you mean by degenerate binary tree? It skews into one particular direction, which means this can be like this. This is a degenerate binary tree. It can't divide here. This is wrong. Right? This is degenerate binary tree. And finally, we have the balanced binary tree, balanced binary tree, where if you have n is equal to 8, we take the log of it, where log is equal to 2 of 8, which is 3, right? So the height should be 3. This height should be 3, which means from the root node, it should have a height like this: 1, 2, 3 from the root node. Keep this in mind. Okay, so that's it. We have completed the binary trees. So many congratulations, whatever. See you in the next one. Bye.